afternoon, everyone. Welcome back to NSR Programmer Machine Learning. This is day 3, and our focus today is on support vector machines, which is usually abbreviated as SVM. We're going to cover the concept of SVM, that support vector machines, including hyperplanes, support vectors, and margin maximization. As usual, we're going to be doing a live coding demo with Python, using an iris dataset to train an SVM, classifier, evaluate it with precision, recall their F1 score, and ROC curves, and learn about gold standard evaluation technique, which is cross-validation. So thank you once again for joining us. Don't forget to like the video and subscribe to the channel. So let's define some terms just to give us a better understanding of what we're focusing on today. So what is a support vector machine? A support vector machine is a supervised machine learning algorithm that finds the optimal boundary, which is the hyperplane, separating class groups by maximizing the margin between closest points that are called support vectors. Now, that's as best as I can define what a support vector machine. And in that definition, I mentioned terms that were hyperplane and support vectors, and then you had something like margin. So what is a hyperplane? The hyperplane I can define it as the decision boundary that separates classes in the feature space. And then support vectors, those are the key data points nearest to the hyperplane that influence its position. And then the margin is the distance between the hyperplane and the nearest support vector, maximized in the support vector machine. When we're defining precision in support vector machines, precision is the ratio of true positives to all predicted positives, and it measures exactness. Then we have a term called recall. Recall is the ratio of true positives to all actual positives, and this one measures completeness. So precision measures exactness and recall measures completeness. The F1 score is the harmonic mean of precision and recall, balancing both those metrics. Then the ROC curve is basically a graph showing trade-off between true positive rate and false positive rate at various thresholds. And then cross-validation is the technique to evaluate model reliability by training and testing on multiple data splits. So let's look at our demo then. Okay. So yeah, I'm going to type out the code and then we'll break it down line by line at the end. Dataset to So maybe someone could be asking where I'm getting that dataset from, the iris one. The iris dataset loaded basically that first line after the inputs, line 8, is loaded by iris. It's a classic, basically it's pre-packaged, it's a pre-packaged dataset included within the scikit-learn Python library, right? What you call scikit-learn here, or sklearn. So it's not loaded from like an external file or URL by default. So basically scikit-learn provides it as part of its datasets module. So that's where our dataset for today is coming from. that's it. Now let's break down what's happening line by line. Of course, from the inputs, from the first input, that loads the classic iris flower dataset. And then line 2 splits the data into training and testing sets. That's what the input is for. Then you notice it also has the cross validation score. Yeah. The cross validation score input is to perform cross validation to better estimate model performance. And then the SVC input, that's the support vector classifier model that we're training here in our script. And then line 4, classification report. That provides detailed performance metrics like precision, recall, F1 score, and accuracy. The plot ROC curve, that plots the ROC curve for classification quality analysis. And then my guys should be familiar now with the matplot library, pyplot or python plot. That's used for creating the plots and visualizations. That's line 5 here. Then from line 7 to line 9, so we load the iris dataset into the variable iris, then x holds the features, that's the input variables, which are the measurements of, let's say, sepals and petals for each flower instance. So we're dealing with flowers, and then y holds the target labels, which is the output variable. The y is the output variable. It holds the target labels, which are the species of each iris flower encoded as numbers 0, 1, 2 for 3 species. So that's line 7 to 8. Line 7 being the comment telling you what's happening, that we're loading the data set. And line 11 to 12, we're splitting that data set. So like we showed you yesterday, we split the data set. Part of it is for training and part of it is for testing. So same here, we are randomly splitting the data set into training, which will be 75% for training, and 25% for testing. So the model will learn from the training data, and then we will test its predictions on the unseen test data, which is 25% of the data. Again, like we covered yesterday, this here basically fixes the randomness to make the results reproducible. And then let's continue line 14 to 16. Line 14 being a comment. So what's happening there is it initializes the SVM model. Excuse me. The support vector machine, which is a supervised machine learning algorithm that finds the optimal boundary, which is the hyperplane that best separates the best classes by maximizing the margin between them. The probability being equal to true enables probability estimates needed later for plotting the ROC curves. The model is trained using the fit method. Yeah, that's the fit method. On the training features, which is X train, and the labels Y train. Then keep going down from line 18 to 20. Line 19. So line 19 to 20, there we're using the train model, yeah, to predict labels for the test data. This is the test data here. And then the classification report prints a summary including precision, which is how many of the model's positive predictions are correct. It also includes recall, which is how many actual positives did the model correctly identify. And then it also includes the F1 score, which is the harmonic mean of precision and recall, balancing the two. It also includes support, number of true instances for each class, and then accuracy, which is the overall percentage of correct values. So all that is being covered here in the classification report. And then of course from line 23 to 25 we plot the ROC. ROC stands for receiver operating characteristics. So it plots the ROC curve for each class. The ROC curve will show the trade-off between true positive rate and the false positive rate at various thresholds. And then, so a model closer to the top left corner will indicate better classification performance. And then of course we add the title and then display the plot. So we add the title and then the plot show method is for displaying the plot. And then the last bit from 28 to 30, that's cross-validation. So it's performing a 5-fold cross-validation whereby the dataset is split into 5 parts and the model is trained and tested 5 times with different splits. So this provides a more reliable estimate of the model's true performance than a single train test split. And then it prints the accuracy scores for each fold and the overall average accuracy. So that's our script for today, the breakdown. So in summary, what this code is doing is it demonstrates training, evaluating, validating a support vector machine classifier using the iris flower dataset. It then splits the data, fits an SVM model to learn class boundaries, predicts labels on unseen test samples, then generates detailed classification metrics like precision, recall, and then it visualizes the model performance with ROC curves and then further assesses generalization with 5-fold cross-validation. So this example that I've typed out basically illustrates not only how SVM works, but also emphasizes the importance of multiple evaluation tools beyond basic accuracy. So it will be giving new learners a well-rounded introduction to classification, model development, and validation. So that being said, I can run the script and then show you the results. So we have an error here. So it's saying it can't import plot. So I'm having an input issue. I should be able to fix that. So it might be an issue of deprecated version. Let's try again. So the print works, but the plot is still failing. And 23. Okay, so there turns out I have to plot the RSE curves one class versus rest by manually computing the RSE curve per class using the probability scores or decision function. So I have to get back into the script and modify it a bit. Alright, alright. Before I was just looking to make sure. Yeah, so let me explain the new additions. Yeah, so I added line from line 13 to the iris dataset has 3 classes, which are species, and they're labeled 0, 1, and 2. That this label binarize converts these multi-class labels into a binary matrix, which is the 1V rest format. So for each test sample, it creates a row with 3 columns, 1 per class, and then it sets 1 in the column corresponding to the true class and 0 elsewhere. This format is needed for the RC curve calculation because the RC function expects binary labels for each class separately. And then from what else did I add? Yeah. From here all the way up to the plot. So let's first break down this. So that creates empty dictionaries to hold. So FPR, false positive rate, is the x-axis of the RC curve. The true positive rate is the y-axis for the RC curve. Then the RC curve underscore AUC, is the AUC stands for area under the curve. So the area under the curve value summarizes the loop. So from 0 to 2, it computes the FPR, which is the false positive rate, and the TPR, which is the true positive rate, arrays comparing the binarized true value predicted for class I, and then it calls the area under the curve to calculate the area under the curve. So yeah, it calls this, yeah, to calculate the area under the curve, which is the RC curve for the class I. And then from here up to there, we are creating a new figure for plotting. Then it assigns distinct colors to each class curve for clarity, and then it plots the curves for each class with appropriate labels showing class index and the area under the curve score. Then of course we plot. So from here, yeah, that whole part there, it draws a dashed diagonal line representing a random guess classifier baseline, sets axis limits and labels for readability, adds a plot title, yeah, and a legend for identification, and then shows the plot in a window. Those code lines transform multi-class labels into binary 1 verse rest format to calculate the RC curve individually for each class. They compute false positive and true positive rates and plot the RC curves on the same graph, visually summarizing the classifier's performance per class. The diagonal line then shows what random guessing would look like, predictive power. So I'm hoping okay. So let me see if you guys are seeing. So I think you can see the curve. It has managed to print, and then we have our results.